Hello guys, welcome back to Mason African Motives. Still working on our power machines and 5 revisions. In this case, we shall be trying by all means to have a full paper revision, which was from the question paper of August 2023, being a request from our members. So this is a platform that you can also be able to request the topics to work on or the question papers to work on. So make sure that you join the membership family so that you help us also to grow our channel each and every day. So we're not going to waste much time, guys. This is August 2023 exam. The requirements that you need here is the steam tables and also the superheated steam tables. We have that, so we shall see how to use those tables in calculations of steam and maybe on condensers, so forth. All right. So, and also your instruction, make sure that you understand your instruction, of which everything here is clearly given. So we're not going to waste much time, guys. Let us quickly rush through our questions and see what we're given and how are you supposed to attempt these typical questions. The first part was on question number 1, which is to list any 4 examples of governors. So we talked about this on the governors that we have what we call a watt governor. So we've got a watt governor in this case. We also have a Porter governor. We also have a Hartnell governor. That's a Hartnell governor, which is a spring loaded. This one is which is a spring loaded in this case. Then we also have the L'Oreal governor in this case. I do not know how you pronounce this. All right, so these are the governors that we have that we are required to know in our syllabus. All right, so that was the first part. Let us check the second part, which of 1.2. Name 2 types of air compressors. So remember, for air compressors, it can be a reciprocating. So you can have a reciprocating air compressor, or we can have it as a rotary air compressor. We can have it as a rotary air compressor, which is also referred to as a centrifugal. So this is a centrifugal compressor. So that was the condition that we are given there. All right, let us see. 1.3, we have got the information that we are on the boiler part. Name 4 particulars to be marked or stamped on the shell of every new boiler according to the regulation of C95. Remember, if you're dealing with a boiler, you are supposed to have the particulars to be, the details to be written on it so that you'll be able to know. And these are the details that they are asking you, which refers to the manufacturer's name. So you're talking about the name of the maker in this case, the name of the maker, which is the manufacturer's name. We also refer to the factory number. We can be talking about the factory number in this case. We have got the factory number. We can also talk about the year of construction. When was it built? That is the year of construction. So we're going to refer to the year of construction. Okay, so that's and also the design pressure, which is supposed to be given is operating pressure and so forth. So we've got the design pressure, which is measured in pascals in this case. We also have the design pressure. All right, so we're gonna have our design pressure in this case in pascals. All right, so we are going to be given this in pascals. So those are the details that you are supposed to have, or the particulars that you are supposed to have. All right, so let us move on to question 2, which was on gases. In this case, the application of thermodynamic of gases, whereby all we need, guys, is the information that you will, and to use your formulas properly. So let us check and see. We are given sum 0.8 kilograms of a gas at a pressure of 120 kilopascals and a volume of 1,8 cubic meters is expanded according to the isochoric process, whereby you're talking about having a constant volume, which is also referred as the isometric process. All right, then the gas then expands isothermally. So there are two expansions here. We've got the first process, then we've got the second process of the isothermal, whereby we have got the constant temperature. All right, then specific of this and specific of that. All right, so meaning to say we've got two processes that are happening here. Let us try to indicate them properly. These are two processes that are happening. So we've got two stages that we are going to take. In fact, from, let us just say stage 1 to 2. Then we've got the stage 2 to 3. All right. The stage 1 to 2 is a condition of this part of the isochoric process. All right. Then let us just try to indicate it properly here. So this is the stage of the isochoric process. In this case, which I referred also as, they can refer to this as the isometric process, whereby the voltage is the same. So we are simply saying V1 is equal to V2. There, the voltage is constant, meaning to say voltage at the first and at the second will be equal. Then the second process that after this was the isothermal process. So we have got the isothermal process from 2 to 3. It is now under an isothermal process in this case. All right, so we've got an isothermal process, whereby we're talking about temperature in this case. All right, so let us refer to this. The temperature 2 is going to be equal to temperature 3. That is the condition that we are supposed to understand. So these are two stages that we have. All right, so let us track our information. So we've got the mass of the gas, which is 0.8 kilograms. So this is our gas. The mass of it, it's 0.8 kilograms. All right, then also we are given the pressure at the inlet at a pressure of 120 and a volume of 1.8 cubic meters. So these are the conditions of the inlet. It is entering at 120, having a volume of 1.8. So these are the conditions that we have here at the inlet. So we're given P1, which is the inlet pressure of 120 kilopascal, and also given V1, which is 1.8 cubic meters. But remember, we said V1 is equal to V2. So we are also having V2 from this condition, which is also 1.8 cubic meters. Since these two, they're equal. So that is the condition that we are going to obtain in this case. All right. So, all right, let us see from the other part that we are given. Now we are given it is expanded according to the isochoric process to a pressure of. So this is the second pressure, which is our P2 in this case. All right. At this stage, we are also given P2. It expanded to a pressure of 180 kilopascal. Under this isochoric process, these are the conditions that we have. Then after that, we are given the gas then expands isothermally to a volume of, from the isochoric process, it is now expanding to a volume. So this is the third voltage that we are going to have after the whole expansion. All right, so this is here we are given V3. So here we are given V3, which is 5 cubic meters in this case. But remember, we said V1 is equal to V2. So from the second stage to the third stage, the volume we have, which is V2. So V2 we have here, which is 1.8 cubic meters. And also the temperature that we're going to calculate here is going to be the same, because we are saying the temperature 2 and temperature 3 will be the same. So we are going to use temperature 2 for temperature 3. We shall see that one later on. So that was the information that we are given. So we only have this, and all right, so that's it. That's what we have for now. And we're also given the specific heat capacity at constant pressure, which is Cp, and at constant volume, which is our Cv in this case, all right? So we've got Cp and Cv. All right, let me just try to write this in a different mark because they are not part of these two, like they are shared between these two. So let me just try to have it like this. So remember, we had the mass there of 0.8. All right, so from those values, we've got to constant volume, which is, right, the first one was Cp to constant pressure. Remember, it was Cp. According to constant pressure, that was 1,008 kilojoule per kg. Then we also have Cv to constant volume, which was 0.72 kilojoule per kg. So this information is going to be related to both condition, whether we are in the isochoric process, we are in the isothermal process. We are going to relate this information to these two. All right, so let us check the first equation that we are given here. The first equation we are given to calculate the following, the characteristic gas constant in this case. All right, so what I'm going to do is to try by all means to bring you guys the formulas, all the formulas actually that you're going to need under each and every process so that you do not struggle on your revision. But anyways, we're given the characteristic gas constant, which is R in this case. How are we going to obtain R from this information that we're given? So remember that R can be found from the Cp minus Cv. Also, you are given this in your formula sheet. I want you to see here so that you work with me. Also, if you check on your formula sheet here, we've got these formulas. Actually, this is your thermodynamics of gases, thermodynamic of gases, all these formulas that we have here, all these formulas, thermodynamics of gases that you're working with there, all this part, all these formulas. So you just have to work with the proper formula for the given information. All right. So if you are to check here, we are given that R is equal to Cp minus Cv. So meaning to say we are going to use the specific heat capacity at constant pressure minus at constant volume in this case. All right. So let us have our information here. We're going to have Cp minus Cv in this case. All right. So that was question 2.1. So R is equal to Cp minus Cv. So we're going to subtract, whereby our Cp is 1,008 minus Cv, which is 0.72. So that was going to give us the value of R in this case, which is 0.288 in kilojoule per kg. So these are kilojoules per kilogram. That was how we're supposed to play around to calculate the value of R in this case, okay? That's 2 marks for that. Then we are given the temperature before and after the isochoric process. We need the temperature before and the one after. In terms of the formula that you're going to use when you're dealing with other processes, you're going, let me explain from these formulas so that you just understand. We are going to be working with all the formulas that do not have this n, because here we are not having, our law is not PV to the exponent of n is equal to C. So we are not going to apply anything of this. So this one is totally out. Wherever that we have this n or this gamma, this one, these formulas, we are not considering them. So meaning to say any formula that we have, whether it's P1, V1 is equal to P2, V2, PV is equal to MRT, we can use those formulas in order to answer this question. So they were asked to calculate the temperature. So if we are to check, we can play around this formula here. There is temperature here. We can play around this formula. There's temperature. We also have, where do we have temperature? So these are the two formulas that we have that can give us a temperature. But which one is the best to apply? That is the question. Which one is the best to apply? All right, according to what we have here, we are going to see that according to what we are having here. Let me write down the formulas that we're going to have. So remember, we need the temperature in this case. So that's 2.2. All right, so you're going to need T1 and we're also going to need T2. Remember, these are two temperatures that we need: temperature before and after the isophoric process. And remember, our isophoric process is between the stage 1 and stage 2. So we need T1 and T2. So from the formulas that we saw there, we had a formula that was P1 V1 over T1, which is equal to P2 V2 over T2. But remember, in this process, we said V1 is equal to V2. So if V1 is equal to V2, it means this can cancel and divide because it's the same. So we are going to remain with P1 over T1, which is equal to P2 over T2. This one is going to be difficult for us to use because we have got two unknown values, the temperature 1 and the temperature 2. Let us move on to the other formula. We also have PV, which is equal to MRT. So using this formula, we're going to check where do we have information. Is it on the second part or on the first part? So let us check on the second part. We've got P, we've got V, we've got P1, we've got V1. So meaning to say we can use any. In this case, remember V1 is equal to V2. So here we can use any formula in this case to find what we want. So we're going to use this to find T1, meaning we're going to have P1, V1 is equal to MRT1, so that we can make T1 the subject. So just going to divide by mass times gas constant, mass times gas constant in this case. All right, so that is going to give us T1. So T1 is going to be P1 V1 over MR. So that was just going to be a substitution that you're simply making. In this case, we've got our values: P1, which is the pressure 120, V1, which is 1,8. So we've got 120 times 1,8 over the mass of the gas, which we have here 0,8. All right, so we've got 0,8 times. Then we have got the gas constant, whereby we calculated it, the value of R here, which is 0,288. All right, so that was the condition which was going to give us T1 in this case, and that was going to be 937.5 in Kelvin. So if you are given this, try by all means to play around with the information. Try by all means to play around with the information that you are given. You are calculating for T1. So you are supposed to be working with P1 and V1. That is the concept. If you were to say you are calculating for T2, it means also what you are supposed to be working on, the pressure, is supposed to be affecting the second condition, which means we are talking about P2, and also we are talking about V2. But in this case, remember we said V1 and V2, they are equal. So if V1 and V2 are equal, it means we are going to have the same answer. All right, so let me explain this way what I'm trying to say here. We are supposed to calculate T1 and T2. So from this formula, we saw that we also have P2 and V2. So we can still use the same thing to calculate for T2. It means for T2, so this I'm just going to write, or because I want to use this formula again, or let me just write it here, no problem. I'll explain this one because someone maybe could want to use this formula after finding T1. You want to find T2. Yes, you can do that. But already here, we saw that from our subject here, T1 is equal to P1 V1. So it means T2 is going to be equal to P2 V2 over MR, because it will be P2 V2 T2. That is the condition. So meaning to say at the end, our T2 was going to be P2 V2, whereby P2 here is 180, V2 is 1,8. So we're going to have 180 in this case times 1,8 over the mass, and this gas constant are the same, just like the previous part. We've got our mass of 0,8, our gas constant of 0,288. So that was going to give us the temperature T2, which was going to be 1406.25 in Kelvin. So which is the same answer that you must obtain if you are to use this formula here that I listed here. So let me just have this one. So, or we can calculate the same T2 that we calculated by this formula. We can just make T2 the subject. That's gonna be T2 times P1, which is T2. P1 is equal to multiply this, which is gonna be P2 times T1. So we can divide by P1. We can divide by P1 in this case. That means T2 is going to be P2 over T1 over P1. So this is another formula that could have given us the value for T2 in this case. We've got P2 and T1 here. So P2 is 180. So that was going to be 180 for P2 times T1, the one that we calculated here, which is 937.5 over P1. Remember, P1 here was 120 also from the information there. So this is going to give us T2, which was going to be 1406.25 in Kelvin. So as you can see, we are obtaining the same answer from different formulas. So as long as you are using the right formula, like I'm saying, as long you are using the right formula, you obtain the same. It's not like this is the right formula or this is the only formula to use. There are so many ways that you are going to apply or that you're going to use. All right, let us check what was the second, what was the other part of the question here. We calculated both here, that is the temperature before and after, then the pressure after the isothermal process. We are no longer in the isochoric process, we are now in the isothermal process. And in the isothermal process, we are considering from the stage 2 to 3. That is our isothermal process. So there we need the pressure after the isothermal process, meaning to say we are supposed to calculate P3 in this case after the isothermal, because isothermal is starting at stage 2 to 3. So after, it means we are supposed to calculate P3 in this case. All right, so what is it that we have? Remember, we have got something here, P2. Remember, P2 is 180 and P2, we are starting with P2 here because this is the second stage. So we have got P2 here, which is 180 kilopascal. Also, we calculated T2. Remember here, we calculated T2, which is 1406.25. So we also have T2. We calculated this value, T2, which is 1406.25 Kelvin. But we said this is an isothermal process whereby T2 is equal to T3. So it means we also have T3 in this case, which is 1406.2 Kelvin. So the question is, we are supposed to calculate P3. All right, so which is going to be the best formula to apply in this case? All right, so as we can see here, we can use the same formula, this one, P1, V1. So, all right, we can use the same formula or the same concept of that formula that we had. All right, just for the sake of calculations, I'm just gonna use this part because I have written T2 here. So let me just erase this and calculate it here. All right, so sorry for that, guys. All right. So like I said, you can use any formula. This time we are in an isothermal, and from those formulas or from this same formula that we had here, we're gonna use it again to find, I'm just gonna explain it later on. But let us talk about this formula again that we listed before, 2.3. Remember, I listed about the formula about P1 V1 over T1 is equal to P2 V2 over T2. So we are talking about first stage, second stage. This time we are talking about second stage, third stage. So this will be 2, this will be 3, all right? So meaning to say we are going to denote this as P2, then the other one will be P3. So we're gonna have P2 V2 over T2 is equal to P3 V3 over T3. But remember that we are talking about an isothermal whereby T2 and T3 are equal. So if these two are equal, we can cancel this part. So meaning to say we are no longer having this. So we are going to have P2 V2 in this case, all right? So we're going to have P2 V2, which is equal to P3 V3. Even if you use the T with this value that you have, even if you substitute it, it's fine. You're going to have the same answer, but just because they are equal, you can also ignore that part, all right? So remember, we want to calculate P3. So we're going to divide by V3 both sides. We have all these values. So P3 was going to be P2 V2 over V3. So let us substitute our values and see. So we've got P2 in this case, which is 180. So we have this one, that's 180 times V2. Remember the volume here, it's 1,8 from V1 is equal to V2. So V2 is 1,8. So we also have the volume of 1,8 in this case. And also V3, we have it from the information that we are given before. V3 was given as 5 cubic meters from the information. This one we are just given. All right, so that was going to give us P3 in this case, which was going to be 64,8 kilopascal. So that was going to be the value of P3, which is 64,8 kilopascal. So like I said, in order for you to calculate this, it's your choice actually. It's just the choice that you are working or that you are playing with from the formulas that you are given. What you just need is to properly understand what am I given from the information. With the information that you are given, use the proper formula or the corresponding formula that is corresponding to that information. You must use the information that corresponds to the given information in this case. You're supposed to be very, very careful on your information. So according to this information, which formula can we also use in this case to calculate the same pressure that we are having? Which formula can we use to calculate the same pressure? All right, I want us to talk about this formula here. PV is equal to MRT. This formula, guys, it answers a lot of questions, a lot of questions. Let us talk about this formula. Remember, we calculated T1, so I'm just going to take this T1 here so that maybe we might need this later on. So let us just write it aside. Here we calculated this T1. Remember, we got 937,5 Kelvin. All right, so I want to erase this part so that we prove with another method of this same method, actually not another method. Let me do it this way. All right, PV is equal to MRT. So like I said, this formula, it has answered a lot of questions. Let us see how. You want to calculate the pressure, so it must be P3 because you talk about at that stage. So this must be V3 and this must be T3. We have V3 and T3. We've got V3, we've got T3. So you can use this formula. So to find P3, simply divide by V3 both sides, by V3 both sides. So that we are going to have our P3 as MRT3 over V3. So you're going to just have to substitute the information that we are given. We have the mass of the gas in this case. So P3 is going to be the mass of the gas, which is 0.8 kilograms. Okay, so we've got 0.8 kilograms times the gas constant, which we calculated here. So this is our gas constant, 0.288 times T3. From the calculation that we made, T3, we said is equal to T2 because of the isothermal process. We've got 1,406.25. So we are going to use 1,406.25 everything over V3, which is the volume that we are given. Remember V3, we are given 5 cubic meters in this case. So we are going to have the same answer for P3, which is going to be 64,8 kilopascal. Guys, we might use 3 formulas to answer the same thing. So power machines, it's in your hands. Which is the best part to use? That is the whole part of this subject. It's not like you are limited to a certain formula. No, there are so many ways that you can play around. As long we are working from the right thing, we are going to obtain the same, or we are going to have the same answers at the end. All right, let us check the other part, which is we are asked to calculate or to determine the total work done, in this case in kilojoules. Take note, in kilojoules. That was 5 marks. All right, so we need the total work done in kilojoules. So since we have these values, I'm just gonna remove this part again. All right, so let us just remove this part here. So I'm just gonna work from this side here. Let us see. Sorry for that, guys. So you're supposed to be very, very careful with the information that you are given. So remember, P3 there was 64,8. We might need this later on. You do not know. So let me just write it down here. So we got 64,8, and our constant of gas is 0,288 kilojoule per kg. All right, so that's it. The question is to calculate the total work done in this case. We need the total work done in kilojoule. All right. Why are we talking about the total work done? Because we've got 2 processes to be considered. We've got the isochoric process, and also we've got the isothermal process. So meaning to say, we are going to have the total work done in this case as the work done taken in the isochoric process from stage 1 to 2. So you're going to have work done between stage 1, 2, which is the isochoric process, plus the work done that we are going to have between the stage 2 to 3, which is our isothermal process. So how are we going to have, or how are we going to calculate the work done? All right. In the isochoric process, we know that work done is equal to 0. Why is that so? All right, the condition is that in the isochoric process, remember that we obtain work done. Let me explain this way. We obtain work done from the heat that is being added or rejected minus the internal energy. In this case, that is the change in internal energy. So under the isochoric process, it follows that our heat that is being added or rejected is the same as our internal energy, which is the change in internal energy. So these two, they will be equal. So once they're equal, you're going to have a 0 in this case. Please take note. Or we are going to use, if we are going to use the change, the pressure and the change in volume, we are going to see that these 2 volumes, they're equal. So V1 minus V2 is going to give us a 0. So there we are going to obtain a 0. So there's nothing that we are going to have here. All right, let me also take you to the formula sheet. All right, let me take you to the formula sheet, guys. Let us talk this. Let us refer to this here. This is these are some of the formulas that you are given here. Let us explain some of the things here. All right, we are not going to be focusing. Remember, I said we are not going to be focusing with these formulas. We have got work done here, but we're not going to work with this because of the index of compression. We are not yet in that process. So for the work done, we are going to be considering these 2 formulas here that we have. It's either we are going to calculate your work done from the heat and the change in internal energy. But if we are to check now to say under the isochoric process, these 2 values, they will be equal. So if they're equal, it means that we are going to have our work done equal to 0 because it shall be Q minus the change in what? Internal energy, which is going to give us what? Which is going to give us the work done. These 2, they're equal. We are using same values, same values, same values. So they'll be equal in that process. The internal energy and what? Heat. So that is what I'm trying to explain from this part, all right? if you were to use this part again for the work done that we are going to have in the isochloric process, to say it's going to be P1 times the change in the volume. V1 and V2 are equal. So V1 minus V2, that's a 0. So there's nothing that you're going to have. So meaning to say there's nothing that we are going to have in this process, all right? If you are to use, okay, this is the best formula that we are supposed to work with in terms of work done actual, all right? I want us to explain this one. All right, let's explain this one here. I want to explain this one. All right, let me come back here and explain here. You understand me, guys? Why? Because sometimes you'll just write a 0, then you even do not know where is it coming from. Maybe you choose that formula for work done. Remember, from the formula that I indicated, we are saying the work done is equal to that's gonna be P1, P2 V2 in this case, or P1 V1. All right, so we're gonna have it as PV, which is gonna be P1 V1, the ln of V2 over V3. All right, I'm going to V2 over V1, sorry. I'm going to explain in terms of what you are given, in terms of what you are given. If you are talking about the isochloric process, remember V1 and V2 are equal. So the moment you try to substitute your values here, let us just substitute because it would be like, this thing cannot be calculated. Let us just substitute. All right, P1, that's 120 times V1, which is 1,8 times the ln of V2. Remember, V2 and V1 are equal, so it's going to be 1,8 over 1,8 like this. All right, so this one, because of the ln, if these two are equal, ln 1 is equal to 0 from our mathematics, we know that, right? But also, you can just use your calculator at once. Then the work done in the second stage, which is 2 to 3, it means here we are going to, remember, in the first stage, we had 1 and 2. We used 1, 1. So it's going to be in the second stage, this will be 2, this will be 2, this will be 2, and this will be 3. So you're going to use P2 V2. Take note about your formulas, guys. That is on the isothermal process. Now we are talking about this stage of 2 to 3 in the isothermal process. It means the work done there. So this is the work done for the isochloric process, whereby we're talking about V1 equal to V2. Then on the isothermal, we are calculating the work done there. So this one is going to be P2 V2. We've got P2 180 times V2, which is 1,8 times ln V3 over V2, V3, which is 5 over V3, which is over V2, which is 1,8. All right, so this is what you're going to have. So this is the work done in the isothermal. This is the work done for the isochloric process. Isochloric process, like I said, this is going to give us a 0. If you use your calculator here, you're going to have a 0 plus this side, we are going to obtain 331,01500, something like that. So this is going to give us, if we add these two, we are going to obtain 331,015. All right, so that was going to be our work done, which is measured in kilojoules in this case. All right, so remember also the units, the work done in kilojoules in this case. All right, so that's it. The total work done, just have to calculate the work done in 2 stages. The one for the isochloric and the one for the isothermal, you combine them. It is the same thing as this question here, the total internal energy in kilojoules. All right, remember we talked about, we're just passing actually about the total internal energy in this case. But anyways, let us go back to the formulas and see how do you calculate the total, the internal energy. And for it to be the total, you are supposed to calculate the internal energy for the 2 stages. All right, so we're gonna calculate this for the 2 stages. So that is our question 2.5. So we're gonna have the change in internal energy, which is gonna have between the stage 1 and 2. plus the change in internal energy between stage 2 and 3. Okay, so we've got between the stage 1 and 2. Remember, I just said here between the stage 1 and 2, the change in internal energy is equal to the heat added or rejected. Not to say that we cannot calculate, we can calculate it, but it is just the same. All right. So the formula that we have for the change in internal energy from our formula sheet, guys, we saw that is the mass times the specific heat capacity at constant volume. Then we've got the change in temperature, which is T2 minus T1. So if you are working from the first stage, it's going to be T2 minus T1, T3 minus T2. But remember, this is an isothermal process whereby T2 is equal to T3. So it means we do not have internal energy. It's going to give us a 0 in this case. The change in internal energy in an isothermal process is equal to 0. But we are supposed to write your formula as MCV into, it's going to be T3 minus T2. This is what we're supposed to have, but T2 and T3 are equal. So that is going to give us a 0. All right, so let us substitute M, which is the mass. Here it's 0.8 times CV, which is 0.72 times the change in temperature, which is T2 minus T1. So remember, T2, we have it 1406.25 minus T1, which is at 937.5. All right, so that was going to give us the total internal energy. Here we're going to substitute, but that is going to give us a 0 there at the end. So meaning to say, we are going to obtain our total internal energy as 270 kilojoules in this case. All right, so that is the total internal energy, which is measured in kilojoules. So that was 20 marks. Yes, we've got 20 marks for everything. So as you can see, if you are working with thermodynamics of gases, just have to be careful with your formulas, use your formulas properly, which is the best formula to use or the suitable formula to apply. That is the concept of your questions. All right, let us check the question of a boiler. So there we've got a boiler, and I think by now we understand these formulas of a boiler. I've tried by all means to bring you questions on boiler calculations. Make sure you also join the membership so that you have access to other questions on boilers, unlimited questions there. All right, question number 3, we are given a steam boiler evaporates 2,500 kgs of water. So it is evaporating this as a steam boiler. It is evaporating this mass of 2,500 kilograms, all right, per hour at a pressure. All right, then the temperature of water entering the steam, entering the steam boiler is, and also the mass of the fuel and the calorific value, and also the specific heat capacity of the superheated steam. You're talking about the superheated steam. So it entered as water. When coming out, it's now a superheated steam. All right, so let us just try to have this, what is happening here. This is what we have. This is what we have. This is our boiler here. All right, so we are talking about a steam boiler plant in this case, which is actually a superheater, because this steam, when it is coming out, it's being superheated. So what are the conditions that we are given? All right, so this is the mass of water. It does not affect. Let us just write it aside. We've got the mass of steam in this case. Sorry, the steam boiler evaporates 2,500 of water, which is it will be steam in this case, which is the water that will be heated at 2,500 kilograms per hour. All right, so we are given also at a pressure of, so meaning to say this boiler, as it is affecting, it's affecting at a pressure of 1,350 kilopascal, and a temperature of, we're talking about, when this is the steam that we are talking about. So this temperature, which corresponds to the pressure of the boiler, is the superheated steam that we are talking about. So it's going to be TSS, which is 260 degrees Celsius. Then also the temperature of water entering the steam boiler. So given the temperature entering, so we've got two stages that we are going to consider here. Got the first stage, also the second stage. So the second stage, since it is being superheated, it is going to be for the superheated, and this one is for the water in this case. So this water is entering at 26.7 degrees Celsius. So we are given T1, which is 26.7 degrees Celsius, which is actually representing TS, which is our saturation temperature. In this case, we're given the saturation temperature. All right, then we also have the mass of fuel, which is 400 kilograms per hour. So we've got the mass of fuel here, which is 400 kilograms per hour. Then also we have got the calorific value, which is 35,000 kilojoules per kg. So we've got calorific value 35,000 kilojoule per kg. So this is what we have. Then the specific heat capacity of the superheated steam is 2 kilojoule per kg Kelvin, which is supposed to be per kg degrees Celsius, because we're going to use our temperature in degrees Celsius. So take note about that. This is supposed to be in degrees Celsius there. So given the specific heat capacity, which is 2 kilojoule per kg Kelvin, but this does not affect, but we are supposed to be given in degrees Celsius. Take note of that information. So the question was to calculate the boiler efficiency. 7 marks for that. All right, how are we going to have the boiler efficiency? All right, like I said, this question, guys, I've been talking about this, so it's not like the first time to have this type of a question, but anyways, let us just see how we're supposed to have our question. Remember that the boiler efficiency, we just have two things to consider: the enthalpy of for this superheated steam and that of water. So the only change in energy that happened is between the two stages. So the efficiency is going to be taken between those two stages that you are taken, that you are given. So it's gonna be mass of steam into H2 minus H1 over, gonna have the mass of fuel times the calorific value, that is be 100%. You are given this in your formula sheet. So here we are considering two stages. It can be a condition. Please do not confuse on a condition whereby you are given maybe there are three stages that you're going to have. We've got one, we've got two, you've got three. And you're asked to calculate the efficiency of the plant. The efficiency of the plant is going to be the last stage, H3 minus H1 times 100%. That will be for the whole plant. But in this case, we've got two stages, 1 and 2. So it's going to be H2 minus H1. All right. So that is how we are supposed to have this. So here we do not have H1, which is our HF at this temperature. So H1 is HF at this temperature. Then H2 is for the superheated steam. So you're talking about H superheated steam. So we have to calculate these, right? So HF, we're not going to calculate, we're just going to use our, because we're given temperature, the saturation temperature at this temperature. So that's at 26.7 degrees Celsius. What is going to be the value of HF? All right, so we're going to need our steam table at 26.7 degrees Celsius here. All right, so this is what you need. You're gonna work with the saturation temperature. Then we need the corresponding value of HF. So we need at 26.7 here. At 26.7, our value for HF is 112 kilojoule per kg. So take note, this is in kilojoule per kg. The pressure there is 3.5. So maybe you were given the pressure, you're going to have the same thing. So we are going to have 112, which is our HF. So our HF here is 112 kilojoule per kg from this temperature that we are given, our saturation temperature. All right, so that means we've got H1. Now we need H2. Like I said, H2 is for the superheated steam. So you're going to need a formula in this case to calculate H2, which is H sup. Remember, guys, that H sup is given as H sup is given as Hg for the dryness for the dry steam in this case into the specific heat capacity times the superheated temperature minus the saturation temperature at the pressure that we are given of the boiler, at the pressure that we are given of the boiler of 1000 at pressure of 1350 kilopascal. We are supposed to have the value of Hg there. TSS and CP, we're given these values here, so just gonna substitute them. So that was going to give us H sub. So I'm just gonna refer to this pressure, 1350 kilopascal. So where do we have this one? I think along these values. So you consider pressure this time. You are working under this pressure here. That is where you are going to consider. So we need the value of Hg there and the value of Ts. Remember, we said Hg and Ts, all right? So where is 1350? This is 1350 here under the pressure. So you're going to take under the pressure 1350. That is where we need our values here. All right. So, all right, what is our value there? So the value for Ts, all right, Ts here is this column. So this is our temperature, Ts, which is 193.4. So that is the value, 193.4 degrees Celsius. Remember, our temperature is in degrees Celsius. So that's 193.4. All right, then we also need the value of Hg from that Hg here, which is at 2787. This is the value of Hg at this pressure that we are given. So we've got the value of Ts and the value of Hg in kilojoule per kg. All right, so we are going to take these values back to our formula so that we calculate our H sub in this case, which is the superheated specific superheated end up in this case. So we saw that the value of Hg there was 2787 plus specific heat capacity, which is 2 into TSS, which is 260, and TS from the pressure here, we got 193. Okay, we saw that it was 193.4. So that is what was going to give us H sub in this case, which was going to be 2920.2 in kilojoule per kg. All right, so let us try to substitute this into our information. So H sub is our H2 in this case. So H2 is equal to H sub, which is equal to 2920.2 kilojoule per kg. So with this information, we are done. Gonna calculate our efficiency. With this information, it is enough to have our efficiency in this case. So the efficiency of the boiler was going to be the mass of steam, which is 2500 times H2, which is H sub in this case, which is 2920.2 minus H1, which is HF at the saturation temperature of 26.7, which gave us 112 kilojoule per kg. All right, so since these values for H2 and H3 are in kilojoule per kg, it means your calorific value must be also in kilojoule per kg. So this one is already in kilojoule per kg. Sometimes they give you in megajoules per kg. You have to change that to kilojoule per kg. All right, so the mass of fuel here, we have got 400 times the calorific value in kilojoule per kg, that's 35,000 times 100%. Okay, so that's it. We're going to have the efficiency of the whole plant, which is the efficiency of the boiler in this case, which was going to be something like 50, so that was 50. 50,146,428, something like that, which is 50,146%. Okay, to 3 decimal places, our efficiency in this case. All right. So easy. Just have to know your formulas, which one to work with. That is the most important part. Then we've got the equivalent evaporation, and at 100 degrees Celsius. Remember, I said this, the equivalent evaporation is calculated at 100 degrees Celsius. All right. So also we've got the formula for the equivalent evaporation from your formula sheet. So this one, I'm not going to waste much time. We have got this formula for the equivalent evaporation at 100 degrees Celsius, which is given as the mass of fuel into H2, the mass of steam, sorry, into H2 minus H1 over the mass of fuel times 2257. All right, so this one, the only part that is changing is that you are simply multiplying by 2257, whereas here you are using the calorific value, and this one is not efficient, so you do not multiply to 100%. All right, so that's it. Our equivalent evaporation at 100 degrees is gonna be, so we are just repeating everything as it is. We've got ms H1 H2 H1 mf. So we are just repeating what we wrote before. 2500 into that will be 2920,2 minus H1, which is 112, everything over the mass of fuel, which is 400 times we multiply by 2257. All right, so that's, we are given this in our formula sheet, so do not worry about that. So this is our equivalent evaporation, which was going to be 7,77636, which is going to be 776. We've got 7736, so it's gonna be 776. All right, so that is our equivalent evaporation from the mass of steam. We're gonna have kg steam from the mass of the fuel. We're gonna have per kg fuel. All right, per kg fuel in this case. Okay, so that is it. We have got everything that was needed on this boiler part. All right, so that was many marks, 10 marks for that. So they actually do ask something of this, we actually talked about this, so it's not something that is new. Let us just continue to revise as much question papers as we can. But as you can see, that was the content of the question. Let's see the other part of question 3. Okay, all right, there we are. The other part of question 3 here is about 4 kgs per second of feed water enters a boiler. It's a boiler again. All right, what are they trying to do, these guys? Okay, let's see. It's a boiler again that we are having. So this time they are saying about 4 kilograms per second of feed water is entering a boiler. All right, so let us just have the same sketch, just like what we had before, and see what we are having this time. So this is our boiler here, and we have got it enters the boiler at this and leaves 88% dry at. All right, so this one is no longer going to be a superheated. It's because it's 88% dry, which means we're talking about enthalpy of wet steam. Because if it is 88% dry, it means there's a percentage of being wet. So it is no longer superheated this time. So here it's gonna be wet steam. So here we are going to have at the first we've got our water, then at the end it is going to come out as wet steam. So you're going to be talking about H wet. It's not a dry steam. It's not dry steam. It's not superheated steam. It's H wet. It consists of dry and wet at the same time. All right, so the first stage and our second stage are given here. The mass, so we're given the mass per second for kilograms per second, okay, for feed water, enters the boiler at 25.7 degrees Celsius. So it is entering at a temperature of 25.7 degrees Celsius and leaves 0.8 and leaves at 88% dry. So you're given the dryness fraction of 0.88 at a pressure of, we are now talking about the pressure after, which is 1,700 kilopascal. The specific heat capacity of water, take note, this time we are given the specific heat capacity of water. Be careful if you check, there's a question that these are supposed to be kilojoules, all right? It's kilojoule per kg degree Celsius. Remember what I was saying? This is supposed to be per degree Celsius. These guys, they are full of mistakes. This is supposed to be kilojoule. All right. So anyway, I talked about this type of a question where you have got the specific heat capacity of water. Whenever you've got the specific heat capacity of water, the enthalpy you're going to calculate it from the product of the specific heat capacity of water times the temperature. This time, take note, you're going to multiply in order for you to find the enthalpy there, which is the specific enthalpy. All right, let us see what was our questions there. Actually, they're asking about this. All right. 3.1, calculate the specific enthalpy of the fluid entering the boiler in kilojoule per kg. The fluid entering its water. So the specific heat capacity there is going to be the product of, the heat, which is the specific enthalpy, is going to be the product of the specific heat capacity, temperature of water. In order for us to have our answer in kilojoule per kg, because we are given this to in kilojoule per kg. If they wanted us to find this in kilojoule per second, we're supposed to multiply by the mass in kg per second. So you're not considering the mass. In order for us to have kilojoule per kg, the mass is not involved. So that's why I'm saying you simply multiply the specific heat capacity times the temperature, because we talked about a certain question where we multiplied by the mass. It was of the units that were given there. You must be careful. All right, so this is our H1 at this stage. You can just write as H1. So it means H1 is going to be the specific heat capacity of 4,187 times the temperature of 25,7 in degrees Celsius. It's given per degree Celsius. So take note, if they make an error to write the Kelvin, it's just that error is supposed to be degrees Celsius there. So you're going to have 107.6059. So 059, which is going to be a 0.6 in this case, all right, in kilojoule per kg. So that means we have got H1 here, which is 107,606 kilojoule per kg. We are given the specific heat capacity of water, so that's why we are supposed to have to consider that. If it was in kilojoule per second, we consider now our mass in kilojoule per kg, so in kg per second, so that it will cancel. Remember, I said if you've got kilojoule per kg like this, if you multiply to kg per second, this one and this one cancels, you remain with the kilojoule per second. So if we wanted to write in the kilojoule per second, we're supposed to multiply by the mass. But here, the instruction reads in kilojoule per kg, all right? 3.2, to the specific enthalpy of the fluid leaving the boiler in kilojoule per kg again. So when leaving the boiler, this is where we have the wet steam. This is where we have the wet steam. So the enthalpy that we are supposed to calculate is the specific enthalpy for the wet steam. So we are simply calculating H wet, all right? So that is H2, which is equal to H wet. All right, how do we calculate H wet? Remember, H wet for the specific enthalpy is given as HF for water plus the dryness fraction times HFG for evaporation. So we're going to have HFG. All right, where are we going to find these HF and HFG at the given pressure? So we are taking at a pressure of what? 1,700 kilopascal. At this pressure, we are supposed to find our H wet. All right, so let us check from our steam. 1,700. So this is under the pressure. So under this pressure, we are going to need HF as we saw, and also HFG under the pressure. So we are going to check the pressure of 1,700. All right, so this is where we have 1,700 here. All right, so that's 1,700. Sorry for that, guys. All right, 1,700. This one. I'm just gonna have this here. All right, so we're gonna take the whole of this part. All right, so you need the value of HF there and HFG. So this is where we have HF and HFG along this column here, HF and HFG here. So that's down here at 1,700 at this point and at this point. So we've got our HF and our HFG in this case. All right, remember HF 872 and our HFG is 1,922. So these are the values that you're going to substitute there, HF and HFG. So we obtained, so you're going to have our H wet. HF, remember, we got 872 plus X, which is our dryness fraction, 0.88 times HFG. We got 1922. So it's just substituting there. So that was going to give us H wet, which is 2,563. So it's going to be 563.36 in kilojoule per kg. So it will be in kilojoule per kg. The moment you want to write in kilojoule per second, you have to multiply by the mass. But the instruction is in kilojoule per kg. So you're supposed to end it there. All right, take note about this. What I'm trying to say here, they are saying the heat transferred to the boiler in kilojoule per second. All right, I talked about the heat transferred. The heat transferred is the change in the enthalpies, in the specific enthalpies that we have. That is the heat transferred. So the heat that is going to be transferred is the change between these two, which is H1 minus H2. Remember, we calculate, all right, so I need this mess here. Remember, we calculated H1 and we also have H2. And the mass in this case, it's 4 kilogram per second. So the heat transferred is the change in enthalpies. That is the heat transferred. So that's 3.23. So that is H transferred. So we're going to have H transferred, which is equal to the change in the enthalpies, which is here we've got 2 and we've got 1. So it's going to be H2 minus H1. So this is what was going to happen. If we subtract these two here, we subtract, we have got our H2, which is our H2, it's 2563.36, which is H2, it's our H wet. Remember, H2 is equal to H wet, minus H1, which is 107.606, like this. We are obtaining the heat that is being transferred in kilojoule per kg, because these units, they are in kilojoule per kg. So meaning in order for us to have this same heat transferred, but in kilojoule per second, that's where you're supposed to multiply, because this will give us kilojoule per kg. So in order for us to have kilojoule per second, we are going to multiply by the mass, which is measured in kilogram, which is taken, sorry, in kilograms per second, so that the kilogram and the kilogram will cancel. Then we have the kilojoule per second, kilojoule per second. So here we are simply going to multiply this part by 4. So if we multiply this, we are going to obtain 9,823.016. It's now in kilojoule per second. So take note how to convert the units to the ones that you are given. Conversion of units. The first part, they were asking us to just leave in kilojoule per kg. So that's why we were not using this mass. Now we have to consider the mass, but that is the only part that can give us per second. The only part written per second is the mass. All right, it is the same thing with this part here, the volume of wet steam in cubic meters per second. In actual sense, the volume of wet steam in this case, all right, where do we take the volume of wet steam? The volume of wet steam, we take it from the dryness fraction that we are given here. This is what we're supposed to have from our dryness fraction. All right, let me just write it here. So be careful on the conversion of units there. All right, so that's 3.24. From our dryness fraction, it follows that the volume is equal to the dryness fraction times Vg. Also, from your formula sheet, I'm not going to waste much time, guys. You have this from your formula sheet here. All right, let's check these formulas here. X is equal to Vm over Vg. So you're going to manipulate this formula here to find Vg. So it's the product that you're going to have. X Vg is equal to Vm. So that means to find Vm is X times Vg. Vg is the volume of dry steam, the volume of dry steam at the given pressure. You're going to have that at the given pressure. So I want to show you here at the given pressure of 1700. What is Vg there? So we are going to have V is equal to X, our dryness fraction, 0.88 times Vg at this pressure. We're talking about the wet steam. So the pressure at the wet steam is 1700. So you simply need under 1700 Vg is going to be, remember this is 1700 and Vg is this one. Vg in cubic meters per kilogram, take note, per kilogram. That's our Vg. So I want the value that corresponds with the Vg at 1700 here. So this will be the value for Vg here, which is 0.1166. So I've got 0.166 in this case, 0.11 0.1166. All right, so let me do this way, 1166. So as we saw that this is in cubic meters per kilogram. So it means we are going to have our answer in cubic meters per kilogram. We are going to have our answer as 0.102608, something like that, which is in cubic meters per kilogram. But here they are said this is supposed to be in cubic meters per second. What is it that we are going to take which carries per second? The only part that has got this is the mass, which is kilograms per second. So in order for us to obtain cubic meters per second, we must multiply by something that is measured in kilograms per second. Since we are given cubic meters per kilogram times, if we multiply by kilogram per second, kilogram cancels, we are left with cubic meters per second. So we are supposed to multiply this by the mass. The moment we multiply by our mass in this case, and what is our mass here? 4 kilogram per second. The moment we multiply by 4 kilogram per second, it means this whole part is going to be left in cubic meters per second. All right, so take note about this. So that was going to give us 0.4104 and so on and so on. 0.4104, which is cubic meters per second. To 3 decimal place, this is not going to affect. So you can even write it 0.410 in this case. All right, in cubic meters per second. That is to 3 decimal place as per instruction, or you can just write this 4 decimal place because you just avoid, but one is the same thing, guys. Do not worry about rounding off of the answers as long you have the exact thing, the exact calculations, and you are showing your calculations properly. That is the most important part. So that was it. Question 3, 60 marks. Let us see what we have on question number 4. Question number 4, it's on the condenser. So this part, I actually worked on this one. So I just hope with time, just gonna come back to you guys and work out. It's gonna be actually a combination of, it's going to be a combined video, or there are going to be separate videos on condensers and also on the calorimeters. That part you need to understand and work with it carefully. All right, so here we are given some of the information. A surface condenser operates under the following conditions. So we have got the wet steam flow rate, mass of cooling water, operating pressure, the dryness factor, the condensate temperature in degrees Celsius, the cooling water inlet temperature, the specific heat capacity of water, Okay, calculate the outlet temperature of cooling water in degrees Celsius. All right. So this is what I say on your normal simplification. When given degrees Celsius, you are supposed to work with kilojoule per kg degrees Celsius. But even if they write a Kelvin, do not be confused, guys. This is what they do. These guys from department, they just make slight mistakes. They don't change some of the things. They just take it from another question. They change something. They don't change everything. So you just use as it is your temperatures in degrees Celsius in case of not clear of the question. So do not panic on such a condition to happen. Talking about the condensers here, there are two actually different formulas that can be used in calculation of actually there are a lot of things that we can work with. Whether we're talking about the mass of water, we are talking about the mass of steam, the specific heat capacity, the change in temperature, which we are supposed to understand and use in calculation of these condensers. So like I said, I'm going to have a separate video on these condensers separated. All right, so anyways, what is it that we are supposed to know about the condensers? It follows that whenever you are dealing with a condenser, the heat that is going to be emitted by the steam, it will be the same as the heat that will be absorbed by water. I've got two different things, the steam and the water. So we are going to be working with the heat emitted. So this will be emitted by steam in this case, which will be equal to the heat that is going to be absorbed by water. So water will be absorbing. So it's going to be absorbed by water in this case. All right. So from the heat of the steam, it is going to be taken from the mass of steam into H wet minus Hc at the suction point temperature. We are going to have Hc, or there's another formula for Hs plus Hc, all right? So if you use this one, it's going to be H wet minus Hc, which is equal to the heat of water. If remember, I said for water, guys, is the specific heat capacity of water times the temperature that you're given. But because of the mass that you're giving of water, we are going to have as the mass of water times the specific heat capacity of water. This time, you're going to consider the change in temperature. It has changed from a certain value to a certain value, whereby we know that the change in temperature indicates T2 minus T1, or T out minus T in. So this is what you're going to have. So what we need on these formulas was to calculate T2. So in order for us to find T2, let us just find T1. Yes, we can substitute on the formula as it is with T2 minus T1, but it's going to be difficult because we've got a lot of things to expand. So just calculate this one, the change in temperature, all right? The moment you calculate this change in temperature, you know that you can calculate T2 from there, all right? So just calculate what? Calculate the change in temperature first. So if we calculate the change in temperature, it's going to be easier for us to find T2. All right, how to calculate H wet, guys? We've been talking about this. H wet from our boiler, we say this is HF. So you're going to have mass of steam into HF plus X HFG for evaporation. All right, so this is our H wet, all right, minus HC, which is at suction point. All right, so this is mass of water, specific heat capacity of water times the change in temperature. So this part here is just a substitution given everything, but we do not have this. So HF and HFG for the wet steam will be taken at the absolute pressure. So this is at absolute pressure. At absolute pressure. All right. Sometimes they give you the barometer reading and the manometer reading. You take this at those values at the absolute pressure at P is equal to the barometer reading minus the manometer reading times 101.325 over 760, if I'm not mistaken there. All right, but that's it. And for if you are working with a condenser, you're gonna subtract. All right. If you are working with a calorimeter, you're gonna add. But this one, we do not have these values, so we're not gonna consider this. All right. But that is the condition there. Then this HC. So okay. So this absolute pressure here, we are given as the pressure here, the operating pressure. This is our absolute pressure. So we are taking this at 10 kilopascal. So that's at 10 kilopascal. So that's at 10 kilopascal, at a pressure of 10 kilopascal. Then HC is taken at TC, which is at the suction point here at TC. When at the cooling, we're given the condensate temperature, in this case, is 29. So that's at 29 degrees Celsius. At the condensate, you calculate HC. So this HC is HF. This HC is equal to HF at TC. All right, at TC, which means at TC, whereby our TC for the condensate here is what? 29 degrees Celsius. That is at 29 degrees Celsius. All right, so that's at TC, but that TC is at what? 29 degrees Celsius. So you need the value of HF there. So you're going to need our steam tables again. So remember, you're supposed to calculate the outlet, which is T2. So let us substitute and we find, because we have everything, just going to substitute the mass of steam. We are given here the mass of steam, the wet steam flow rate is 3,600. So we are given 3,600 kilograms per hour. So it's going to be 3,600 into HF and HFG at 10 kilopascals. Remember, I said at the absolute pressure. So we need at 10 kilopascals. All right. So let us go back to our steam table. All right, at 10 kilopascals, we've got under pressure here. So we're going to take under pressure. Under pressure, we need HF and we need HFG there, under 10 kilopascal. And this is pressure of 10 kilopascal here. So we are going to need the corresponding value of HF and HFG, which is HF here, that is 192. So the corresponding value at HF is 192. HFG is 2393. These are the values that you're going to take, all right? So we've got 192 and 2392 for HFG, all right? So please make sure you take your values properly, guys, okay? So that's it. So we found out that our HF was 192 and our HFG was 2393, but we're gonna multiply this by X, all right? So which is our dryness factor, and our X here, dryness factor, is 0.82, all right? So that's 0.82 there. So you're gonna multiply by 0.82 in this case, all right? So this, we just took it from our formula sheet, from our steam table, this 192 here, from this pressure, and also this 2393, we just took from our steam, all right, minus HC. So HC also from our steam table, it's the value of HF at 29 degrees Celsius at TC, all right? So at 29 degrees Celsius, what is the value of HF? We need the temperature this time at 29. This is 29 here. At 29 degrees Celsius, what is the value of HF? All right, so we need 29 there, HF. So as you can see, the corresponding value of HF here is 121 in kilojoule per kg. So you're gonna use 121 in place of HF. So that's our HC, is at that temperature that you are given. So that will be 121 here. So it's gonna be 121. Okay, so that was it. So this from our steam table, which is equal to, we are just going to substitute the mass of water. We have everything here from our information, the mass of cooling water. But we have to convert now this one. We have to convert it. We are supposed to have it as kilograms per hour, and this is kilogram per second. So what are we going to do? We've got two ways, or you can just say in an hour, we've got 3,600 seconds. What about in a second? In a second, how many hours are we going to be talking about? So it's going to be 1 over 3,600 in this case. So it's going to be 1 over 3,600 hours, right? So in order for you to convert, you're just going to multiply, divide by this, because you need kilogram per hour, guys. It means over an hour. Here we've got 18 kilogram over 1 second. So per hour, it means I'm going to have 18 kilograms over 1 second. In hours, it's 1 over 3,600 hours. We now have kilogram per hour. So if you do that, you simplify, you are going to obtain, if you divide these two, you're going to obtain 64,800, which is in kilogram per hour. Or on this answer, you multiply it by 3,600. But you have to be careful because it was taken from 1 over, then we multiply to that. All right, so that's 64,800, which is the mass of water. So we have this supposed to be in kilogram per hour. So this was going to be 64,800. All right, times the specific heat capacity of water. We also have this. All right, so we're just gonna substitute here the specific heat capacity of water, 4.1. All right, everything is there, 4.187. So that's 4.187. All right. And like I said, we are going to calculate the change in temperature first. By calculating the change in temperature, it means we have T2 from there. So we are just going to leave this as it is, or you can write as T2 minus T1. You substitute T1 because you're given, but here I'm just going to avoid that. I'm going to calculate the change in temperature direct. How is that direct? Because I'm just going to divide by this throughout by 64800 times 4,187. I also divide this side 64800 times 4,187. So this will cancel with this part. I'm remaining with the change in temperature in this case. So my change in temperature from this simplification is going to give me 26,978, which is 97847, which is 978 degrees Celsius. So if this is the change in temperature, that is not our question here. The question is not to calculate the change in temperature, but the question is to calculate T2. So in order for us to have T2, we are just going to transpose T1 this side. So it means the change in temperature plus T1 is equal to T2. So in order to find T2, which is our question here, we are saying T2 is the change in temperature plus T1. So that's it. We are going to have the change in temperature, 26,978 degrees Celsius plus T1. Remember, T1 we are given on our information here. The inlet, the cooling water inlet temperature, 18 degrees. So the inlet is 18 degrees Celsius. So you use the inlet there, which is at 18. So we are going to add 18 degrees Celsius. So that was going to give us T2, which was going to be 26,978 degrees Celsius. Okay, so no, I'm repeating here. I did not add here. Okay, guys, I'm supposed to add. I'm repeating the same thing here. So I'm just going to add. I'm going to obtain 44,978. I have to add properly there. So make sure that you add properly. You are going to obtain 44,987. 987 exactly. So these are the typical questions that you are going to be referring from or working from. All you need is to make sure that you are understanding your questions. All you need is to make sure that you understand your questions. Read, understand the question, and also manipulation of formulas. You are supposed to be able to manipulate your formulas in order to answer the question that you are asked on that question. You are supposed to manipulate your formula in this case. Make sure that you play around your formulas in manipulation. That is what I'm trying to say. All right. 4.2, it was just the concept of a compressor that we are given here. So let us check what we have. So we have got a single acting, and also it's a single cylinder, a reciprocating compressor. Remember, on the first part, we talked about types of compressors that we can have: a reciprocating air compressor, or we can have a rotary air compressor. So here we are given that it's a reciprocating air compressor, and take note, it's a single acting, single stage. So we are talking about we are not having any effect that we're going to have on our efficiency if we are given the on the speed, which is in revs per minute. And we also do not have that. I considered the issue of a speed. I think it was November 2020 question. You have to check that one so that you see how to apply the speed. In this case, we do not have the speed in these calculations. All right, so let us see what you're given. So you're given that it supplies 0.27 kilograms of air at a pressure of 96 kilopascal and a temperature of 277, the delivery pressure. Then we've got the clearance related to the stroke volume and the index of compression. All right, this is what we have. Let us just try to see here just a smaller sketch. So I'm just going to have a smaller sketch here. Remember here, because we have got a clearance this time, we've got a clearance that is to be considered. So we are just going to have our diagram like this. All right, pardon for my sketch, guys. So it's a straight line. Sorry for that. This is in a straight line. This sketch is a little bit ugly there, but we are supposed to have this just in a straight line. All right, because here it's at the same point, okay, and also at the same point. So remember, we've got our pressure, then we have got our volume. Considering from the first, second, third, and up to the fourth point. All right, which is here. Like I said, these are in a straight line, guys. All right, these are in a straight line. So it means P1 and P4, they will be equal. So P1 is equal to P4. And also here in terms of pressure, P2 is equal to P3, all right? These are not in a straight line. These ones, it's not a straight line there. So it's a curve. This one is a curve, all right? So these are not at the same point. So V1 and V2 are not at the same point. So this is V1. Here we are going to have our V2, which is not important. Then here we're going to have our V4, which is important, and we're going to have our clearance volume at V3. All right, so this is what we just have on our sketch. Maybe we might need any part that we need to talk about. So we've got the inlet and we've got the delivery. So this is the inlet. Then this is at the delivery. So we've got at the inlet, and here we are at the delivery in this case. All right, so we've got the delivery there. So if we are to check according to the information we're given, that this single acting single cylinder reciprocating compressor supplies, we're given the mass per second. So it supplies M of 0.27. Take note, this is kilogram per second of air at a pressure of, so if it is supplying, it is the input. So this is our P1. So we've got P1 at 96 kilopascal, all right, and a temperature in Kelvin. So you're given the temperature, which is also T1 at the inlet, 277 Kelvin in this case. And the delivery pressure at the delivery, we've got 900 at P2. So we've got a P2, which is 900 kilopascal. Then the clearance volume is, take note, the clearance volume is 3% of the stroke volume. All right, so this is it, guys. The clearance volume, which is VC in this case, all right? So the clearance volume is 3% of the stroke volume, which is VS. So 3% as a decimal, it's 0.03 divided by 100. So that is the ratio between the clearance volume and the stroke volume, which this decimal that we see is alpha. It is given as VC is equal to alpha VS. All right, that is alpha being the constant that or the ratio that connects VC to VS. All right, so that is our alpha. We shall talk about that if we have a need in this question. Then also the index of compression is 1,2. So we've got index of compression 1,2. The gas constant R in this case is 0.287 kilojoule per kg Kelvin. All right, so this must be Kelvin because our temperature is in Kelvin, so this is fine. Okay, then 4.21, the effective volume of air. Calculate the effective volume of air. Calculate the effective volume of air. Take note, in cubic meters per minute. Effective volume. How are we going to end up, or how are we going to calculate the effective volume? From this diagram, we were supposed to, if we have got V1 and V4, we're going to have effective volume. This distance that we see in between V1 minus V4 is our effective volume. So if we have got V1 and V2, we're going to calculate the effective volume, but we do not have this. So what are we going to do? We are going to use the inlet conditions. We are going to take from the inlet conditions, all right? So that's 4.21. From the inlet conditions, you are going to apply the inlet conditions to calculate effective volume, which follows that P1 times VE is equal to MRT1 at the inlet conditions. And we need to calculate VE, which is our effective volume. So if we are to use the information that you're given, I want us to just make this the subject. Take note of what we are given in terms of the units. They want us to calculate the effective volume in cubic meters per minute. Take note, this is the instruction they gave us in cubic meters per minute. So this is supposed to be in cubic meters per minute in this case, all right? But here, according to what we have, let us make this the subject. So it follows that our VE, we divide by P1, VE is going to be equal to MRT1 over P1, okay? That is what we are going to have at the end. And if we are to check here, this mass that we are given, here, according to our information, all right, I wrote this mass, where is it? On top here, it's kilograms per second. If we check, this is given in kilograms per second. So it means in our calculation, we are going to have our answer in cubic meters per second, not cubic meters per second. Our answer is going to be in cubic meters per second. So we have to convert it to cubic meters per minute. So it's either you are supposed to just convert from your mass to write it in kilograms per minute, or you calculate your effective volume, you find it in cubic meters per second, then you convert to cubic meters per minute. It's your choice. So that's what I'm simply saying. So let's just say we have to calculate this. We saw the last part. We calculated after converting the units this time. Let us just calculate direct. So the mass here in kilograms per second is 0.27. So take note this value. It's 0.27 times R in this case, which is 0.287 times T1, the temperature in Kelvin. Remember, this is per Kelvin. So you're going to use our T1 which is 277. So we've got a 277 over P1, which is the pressure at the inlet conditions, which is 96 kilopascal. So you're going to have 96 kilopascal. So like I said, our answer is going to be in cubic meters per second in this case, all right? So if we are to simplify this, we are going to have our effective volume as 0.22359 and so on, which is in cubic meters per second. So in order for us to convert to cubic meters per minute, we are simply going to ask ourselves the same thing, just like the previous part. In a minute, we know that we've got 60 seconds. In a minute, we've got 60 seconds. So how are we going to write a second to minutes? So 1 second, if we are to write it in minutes, it's going to be 1/60. So it's 1/60 times a minute. So our answer is now in minutes. So in order for us to have per minute, remember I said this means cubic meters per second, which is 1 second. So to have it in cubic meters per minute is going to be the value 0, whatever that you are having on your calculator, just as it is on your calculator in cubic meters over the second now in minutes is the 1/60. So it's going to be 1/60 like this. So you're going to divide to 1/60 or you multiply by 60. So this is going to give us 13, all right, actually I wanted us to have this aside. Let us have it aside. We need this one because we might need to use this later on. So that's 13,4 for cubic meters per minute. Now, if you convert these to cubic meters per minute from the cubic meters per second that we were having before, or like I said, you could have just converted the mass in the beginning, or guys, as long you are applying the correct conversion, it is going to be considered fine. All right, let us check the other part on under the same question or under the same information. They are now asking us to calculate the delivery temperature in this case, which is T2. At the delivery, we need T2. All right, remember the application of air compressors is just direct to that of or what we use when we are talking about gases. That's why we are talking about this formula that we applied on thermodynamics of gases. So since we are given the index of compression, we've got P1, we've got P2, we've got T1. We can also use the formulas that we know under thermodynamics of gases because it's a direct application. So let us see, there's a formula here which consists of temperature, pressure, and volume at the same time, which you are going to choose here with N, because this time you are having the index of compression. So you're going to choose this part. So since we do not have V1 and V2, we are going to equate, we are going to take these two. We are going to be operating with T2 and T1 to P2 and P1. So this is the part that we are going to take on our formula. All right, so let me just write our formula here. So like I said, we're going to take that part alone. So that's 4.22. So we saw that under T2 over T1, it is going to be in terms of pressure, it is going to be P2 over P1 to the exponent of N minus 1 over N. We're not going to use the volume since we do not have V2. We've got VE for the inlet conditions, but V2 we do not have. So we are going to use this. We are supposed to calculate the delivery temperature, which is T2. So we can just multiply here by T1 to remove this T1. We also multiply this side by T1. So this one can cancel. So that means T2, our delivery temperature is going to be T1 into P2 over P1 to the exponent of N minus 1 over N. So here we're just going to substitute our values. That's T1, which is 277 into P2. We've got our pressure here from the information. That's 900 over P1, which is 96. So we've got 96 to the exponent of N minus 1. So that's our N, which is 1,2 minus 1 over 1,2. So that's it. We are going to simply have this on our calculator done. So just make sure that you use your calculator properly in this case. All right, that's 277 into 900 over, in this case, 96. All right, that's to the exponent of, put a fraction there, that's 1,2 minus 1, then over 1,2 like this. So this is going to give us 402,230, which is 23 in this case. All right, so that's 402,23, and temperature in kelvins in this case. So we're going to have this in Kelvin. All right, so that is how we could have calculated the delivery temperature. We also talked about this formula on the compressors. If you still remember this question, they do repeat it a lot of times, of the delivery temperature. All right, then we have got the 4.23, the volumetric efficiency. All right, on the volumetric efficiency, I want us to consider this. All right, this one I want to explain from the formula sheet, because I talked about this, but we were talking about, we're just referring to two things. If you still remember, all right, let me put this way so that I can explain what I need to explain here. This is the part of our volumetric efficiency. In this case, if you are to calculate your volumetric efficiency, we can use VE over VS, which is the stroke volume that we are given, but we have this, we do not have the stroke volume from the information that we have that on that part, guys. We saw that we do not have the stroke, we are just given a ratio. Do not confuse between this part. All right, let me get you back. I want to get you back to that part here. All right, do not confuse between the information that you are given here about VC. To say VC is 0,03 of VS. You are not given the value of VS. You are not having the value of V3. It's going to be difficult for us. We have to start to calculate these values. The only part that we want here is the efficiency. So we have got VE, but we do not have VS. So meaning to say that formula is not going to be valid. We are going to be limited on that formula. So we have to think of another formula. All right, let me just remove this part. I don't think I'm going to need it anymore. All right, so we are supposed to be thinking now of these two formulas which are left. The same volumetric efficiency can be calculated from this formula, or it can be calculated from this formula. All right, let me explain this. From the second formula that we are given, 1 minus VC over VS, we've got the clearance volume, the stroke volume in this case. So we can apply this because we have got a ratio that we are given between these two. So at the end, VS and VS will cancel. We have P1 and P2, and we have, so meaning to say this formula can work. Alpha in this case is the ratio that we are taking between VC. Remember I said VC is equal to alpha VS. So meaning to say we have the alpha in this case. And RP is the ratio of the pressure in this case, which is taken as P2 over P1. But remember from our diagram, I referred that P1 and P4, they are equal. And also P2 and P3, they are equal. So instead of us having this as P2, which is the ratio of pressure, it can be taken from P3 over P4. We can have this RP as P3 over P4. So meaning to say we have this R, so we can also use this one. All right, so let me explain this back to the information. So I hope you saw the formulas. So I'm gonna just take those formulas and calculate. So since we do not gonna need this, let us remove, because with this one it's not gonna work because we do not have VS, we do not have the stroke volume in this case, so we are limited. So from the two formulas that we saw, I'm just going to start with the first one. So that's 4.23. So our volumetric efficiency from the first formula it is given as 1 minus VC over VS into P2. It was P2 over P1 in this case, all right, to the exponent of 1 minus N minus 1 like this. So here I want us to be careful on this formula. VC over, we have got a ratio that we're given. VC is 0.03 of VS. So even if we substitute in terms of VS, it's going to cancel because we've got VS here. So that's why I'm saying this formula is valid. So we are going to apply it 1 minus VC. Remember that the clearance is 0.03 of VS. All right, so it's going to be over VS into P2. So you're going to have P2, which is 900. So you've got 900 over P1, which is 96 to the exponent of 1 over N, which is 1,2 minus 1. All right. So on this part, as we can see, whatever that you're going to have at the end, we must multiply it by 100%. This is efficiency. So you're going to multiply by 100% at the end. Okay. So if you are to simplify here, the VS and the VS was going to cancel. Here, do not be tempted to subtract 1 minus 0.03 because 0.03 is multiplying this bracket. So you do not subtract. It's like this. 1 minus, all right, let's take it this way. It's like this. 3 minus 2 x, like this. It's like this. Then you subtract, you say 3 minus 2, you get 1. Then you multiply to x. This is wrong. You cannot do that because 2 and x are multiplied. So you simplify this first. So it's going to be 3 minus 2x, which cannot be combined. So you cannot subtract this part. That is the condition that we are having. So you do not subtract these two because this part is supposed to multiply this first. So just use your calculator as it is on this display. Use your calculator as it is. All right, so I'm just going to use the calculator here. This is what I'm trying to say. So on our calculator, let us see. We're going to have 1. So let us just have 1 minus 0.03. So this is 0.03. Open the bracket. Then we're going to open another bracket for 900 over 16. So this is in a bracket like this, raised to the exponent of 1 over. So it's 1 over 1,2. Okay. Then after that, we subtract a 1. So we're going to subtract a 1. We close that bracket. So remember, we closed the bracket of 900 over 16. Then we closed the first bracket that we had, the bigger bracket, this one. So this is going to give us a decimal in this case. All right. That's going to be, all right, 0.16. All right. Here, there's something that I'm supposed to have from my calculation, which is different from what I am having from this calculation now. All right, let me just try have my fraction properly here. All right, let me just have it this way. 1 minus 0.03. I don't know which part did I mistakenly, because I did this on a separate preparation. The answer that I'm having on my preparation and the one that I'm having here, they are different. All right, so this is 900 over 96. All right, that's 96. Close the bracket to the exponent of, put a fraction there, that's 1 over 1,2. 1 over 1,2 like this. All right, then we're gonna subtract a 1. Okay, close this bracket. I think we have it. All right, exactly. So I don't know which part did I just mistakenly indicated. Okay, so this 0.8363 and so on and so on and so on. All right, so you're gonna have 0.836314 and so on and so on. All right, remember that there is 100% that you're having there. So the answer that we are obtaining, just gonna multiply by 100%. So this will be 83,631. 83,631. All right, so you're gonna have 83,631. 631%. All right, so that was going to be our volumetric efficiency in this case. All right, so you have to be careful on your simplification on the calculator. Please, on the calculator there, be careful. All right, but like I said, or like we saw from the formulas that we had there, we have got two formulas that I said we can consider. All right, so because of the two formulas that we can consider, let us try to have another one and see if we are going to have the same thing. Remember the other formula was given as, so you can just have this as, or our volumetric efficiency is gonna be given as, remember was our formula was 1 plus alpha, that was 1 plus alpha minus alpha into RP, all right, to the exponent of 1 over n. So whatever that you're going to have here, going to multiply by 100% since this is efficiency. So like I said, alpha is simply here, we talked about this alpha, say VC is alpha times VS. So alpha in this case is the constant part that you are having percentage, which is as a decimal 0.03. So we are going to have this as, all right. So our volumetric efficiency is going to be 1 plus alpha, which is 0.03, minus alpha 0.03 into the ratio for the pressure, or the pressure ratio, which I said it's P2. So remember I said RP, it's a P2 over P1. But remember that P2 is equal to P3. So it's going to be P3 and P1 is equal to P4. So it is also over P4. So you can take it from what you're given. So since here we are given P2 and P1, we're just going to use as it is P2 and P1, which is 900 over 96. So this is going to be 900 over 96 to the exponent of 1 over n, whereby we've got 1,2. So that's it. We are going to obtain our efficiency from there. So that was another way to obtain our volumetric efficiency. All right, sorry for that, guys. So this is going to give us the same answer actually. So just use your calculator properly here. Let's see what you're gonna have. We use our calculator. This is gonna be, just open a bracket, you're gonna have 1 plus 0.03 minus 0.03 into 900 over 96. So that's 900 over 96 like this. All right, to the exponent of 1 over, that's 1 over 1,2. Right, let's just solve. I do not make a mistake here. All right, so let's see. Yeah, that's gonna be 0.83 something something. Then you're gonna multiply by 100, which is 83.61%. As you can see, we are having the same answer there, 83.631%. All right, so that would be our volumetric efficiency. So as you can see, it's just different formulas having the same answers that we applied. You can choose this one or you can choose this. So that was it, 4 marks for that. Okay, so this is how our questions might be given when we are working with the compressors, and we just have to play around with the formulas. Actually, power machines, it's all about the formulas. You are playing around with the formulas, so do not panic. Just try by all means to understand the information that you're given and how are you supposed to attempt that typical question that you're given. Careful on your answering of questions. It's very, very important to understand your information. Then here we've got the information on the analysis by mass, which is combustion of fuel by mass in this case, all right? Which is an oil fuel sample gave the following analysis. So this is the analysis by mass, whereby we're given the percentages carbon, hydrogen, sulfur, and oxygen. Then if 30% excess air is supplied, calculate the percentage combustion by mass, take note by mass, of the combustion products. We are dealing with the products in this case. All right. So this is what you're gonna have. Remember, we've got carbon, each and every part being heated with oxygen. So meaning to say the products that we are going to expect in this case will be carbon dioxide from carbon and oxygen. We're going to have carbon dioxide in this case, hydrogen and oxygen. We're going to have H2O, which is water. From sulfur and oxygen, we're going to have sulfur dioxide. Then the excess percentage, we've got excess here. So we're going to have excess O2. Then also the nitrogen, which is part of air. So we're going to have also nitrogen, which is part of air. So remember, nitrogen by mass, it contains 77% of the actual mass of air. The actual mass of air. So that is the condition that you're going to have for N2. Then the excess O2 is simply the percentage excess that you're going to have times the mass of oxygen in this case. All right. And these ones, we can have them from our theoretical formula. Remember, we've got the theoretical mass of air that you can have from the formula. So yeah, let's see. Okay, let's see from our formula. Remember, I said there are two formulas that you're gonna use, but here we are not gonna apply the second one. All right, I actually removed that part. Okay, I still have it. Okay, here. So we are going to be applying this formula for the theoretical mass of air, which is simply 100 over 23 times the mass of oxygen. This whole part that we see here, remember I said it represents the mass of O2 in this case, which is the mass of oxygen. So here we've got 8 over 3, which is just as a decimal is something like 2,667. This is 2,667 kilograms of oxygen that we need in carbon dioxide. All right, per 1 kg of carbon dioxide. This is 8 kilograms of oxygen that we're going to need per 1 kilogram of hydrogen. Here there's 1 kg of oxygen that you're going to need. So you have to understand your formula. Then this one, you are going to use it if you are dealing with the hydrocarbons. When you're given a hydrocarbon, this is the best formula that you're going to use. And I explained those two formulas separately. So make sure that you just watch the video so that you understand some of these calculations. All right. So in order for us to have the products, we are going to need the theoretical first. We are going to have our theoretical mass of air and so forth and so forth. So we are going to need that formula whereby we said a mass of air is, this is the theoretical mass of air. All right. So we've got a theoretical mass of air. So this is the theoretical mass of air. All right, seems like someone is tired here. All right, so that's going to be 100 over 23 into 8 over 3. So that it's over 8 over 3 times the carbon plus 8 H2 plus sulfur, which is just 1. So this is a 1 there minus O2. So like I said, this whole presentation that we see here, it represents the mass of O2, the mass of oxygen. All right. So that means, okay, let us just substitute our values. So it's going to be 100 over 23, then 8 over 3 times carbon, percentage of carbon here. Remember carbon, that's 80%, so it's going to be 0.8. So that's times 0.8 plus 8 times hydrogen. The percentage hydrogen, 11%, which is 0.11 if we divide by 100, plus 1 here for sulfur is just 1 kg of oxygen that we have. So it's 1 kg times the percentage of sulfur, which is 5%. So 5% as a decimal, that's 0.05 minus oxygen. The oxygen that we have is 0.04. That's 4%. So it's going to be 0.04. All right, so that's it. So like I said, this whole part is your mass of oxygen. So you can just simplify this part only on your calculator. So you're going to obtain something like 100 over 23 times. This part is going to give you something like 3.023 and so on and so on and so on, which is representing the mass of oxygen in this case. All right, which is the mass of oxygen. You're supposed to write this separate because you're going to need it later on. All right. But if we simplify from this, if we multiply by 100 over 23, we are now having theoretical. Remember, oxygen carries 23%. So air having 100%, but at theoretical values, we are going to obtain this as 13,1449, which is 145 in kilograms. So we've got the theoretical mass, which is not important for us because for us to obtain N2, which is the nitrogen, we need the actual mass of air. So we are going to calculate the actual mass of air. From our excess oxygen that we are given, it follows that the actual mass of air in this case is going to be the mass, which is the theoretical mass that we are given, times 100 plus the excess of air percentage that you are given over 100. So we are going to add the excess percentage of oxygen, that is 30%. All right, so we are going to add 30%. So meaning to say we're going to have the mass at theoretical values, which is 13,145 times x, remember, is 30. So if we add 30, it's going to be 130. So it will be 130 over 100. All right, so that will give us the actual mass of air in this case, which is going to be 17,0885, which is 089 in kilograms. All right, so we have got the actual mass of air that we needed. So I think that's it. Let us talk about the products. So what is the reason of calculating this actual mass of air? It's because we need nitrogen as a product there, which you said it's 77% by of the air by mass. If it is by volume, we are going to be considering 71. 79 from the concept that oxygen will be having 21% and it will be having 79%. Here, oxygen is having 23%, so 77% is for nitrogen. All right, so let us just talk about it, because we need the percentage of the products. So I'm going to just start with that nitrogen because it's the one that also made us to calculate this actual mass. So we said it's 77% of air, which is the actual mass of air. So that's 77 over 100 times the actual mass of air here, which is 17,089 kilograms. So that is going to give us, in this case, the mass of nitrogen, which was going to be 13,159 kilograms. All right, so that will be the nitrogen in this case. All right, so this is our first. Then also let's talk about excess oxygen. From the mass of oxygen, we talked about excess oxygen. So let us just finish on these ones. All right, then we have got excess O2 in this case. So that one, I said it's the percentage excess times mass of oxygen. So it's percentage excess times the mass of oxygen in this case, all right, of which our percentage excess is 30%. So it was going to be 30 over 100 times the mass of oxygen. That's why I was saying you are supposed to indicate on your calculation here, you are supposed to first calculate the mass of oxygen from this part here so that you do not go back to the formula and calculate again. So here we say the mass of oxygen, which is the whole of this part, represents the mass of oxygen is 3.023. So you're going to have 3.023 kgs there. That's 3.023, all right, kilograms. So that was going to give us 0.9069, which is 0.907 to 3 decimal place. I'm just going to round off my values, all of them, to 3 decimal place. All right. Then the other products that we have listed here from the inputs that we have. Remember, we've got inputs, carbon, hydrogen, and sulfur. So we said we're going to have carbon dioxide, water, and sulfur dioxide. All right, so let us see for carbon dioxide. All right, so for carbon dioxide, what you're going to do in this case is, all right, so we need for carbon dioxide, what you're going to do, you take the mass that we have of oxygen, the total mass of carbon dioxide, which is the product. Remember, we said here on our formula, okay, let me explain it this way. This is our formula. We've got 8 over 3C, which is something like 2,667 kilograms. These numbers that we see here, they represent the mass of oxygen. So this is the mass of oxygen that we need, but taken per 1 kg of carbon. So we are going to add 1 kg of carbon to obtain carbon dioxide. So it's going to be 2 plus 1, which is going to be 83,667 kilograms of carbon dioxide. So it means carbon dioxide as a product, it has got a mass of 3,667. So it's going to be 3,667 kilograms times now the percentage, because we are given the percentage of carbon. So we are supposed to multiply whatever that we have by the percentage of carbon. And here the percentage of carbon is 80%, which is 0,8. All right, so you're going to multiply to 0,8. So that will give us the mass of carbon dioxide as a product, all right, which is going to be 2,9336, which is 934. So it's going to be 2,934 kilograms. All right, then we move on to another product, which is water. So that's the fourth one, which is water in this case. So just like carbon dioxide, in order for us to obtain water, we need hydrogen and oxygen. So here, oxygen takes 8 kilograms. So we have got 8 kilograms of oxygen plus 1 kg of hydrogen to give us water. Oxygen and hydrogen to give us water. So it's going to be 8 plus 1, which means we've got 9 kgs of water at the end. All right, so we're going to have 9 kgs of water. So that's 9 kgs of water times the percentage that we have for hydrogen, which is the percentage here for hydrogen is 0,11, which is 11%, which is 0,11. So we are going to multiply by 0,11. That's it. We've got 0,99 kilograms. All right. And if you check there, the last product was sulfur dioxide in this case. All right. So we've got sulfur dioxide. So again, sulfur dioxide is taken from sulfur. So we need to understand this. We need 1 kg of oxygen. This is the mass of oxygen. So we've got 1 kg of oxygen plus 1 kg of sulfur to give us sulfur dioxide. So 1 kg plus 1 kg, that will be 2 kgs of sulfur dioxide. So that means we have got 2 kgs there of sulfur dioxide at the product, but multiplied by the percentage of sulfur. Remember the percentage of sulfur from our percentages, sulfur it's 0.5%, which is 0.05. So that is how you calculate the products. These are the products that you're going to have, which is going to be 0.1 kilograms. So we have calculated, we have stated all the products from the nitrogen, which is part of the air, the excess oxygen, the carbon dioxide, the water, and the sulfur dioxide. So we're going to add these values now. We add everything. We obtain the total of these products. So that was going to give us a total mass of 18,09, something like that, kilograms. So it also depends with your rounding off. How are you rounding off your values? But that's the idea that you're going to have. So in this case, the question was not to calculate the mass, it was to calculate the percentages. So the percentages of the products now are going to be taken from each product over the mass. If you consider nitrogen in this case, we are going to consider to say nitrogen, its mass in this case is 13,159 over the total mass that you're given here of 18.09 times 100%. We are supposed to obtain the percentage which corresponds to nitrogen. These are the percentages now. So nitrogen was going to give us something like 72,742%. So like I said, the rounding off, guys, it's up to you, right? Then we do the same for excess air. In this case, for excess O2, you're going to have the same. You just take this mass over the total mass times 100%. So that was going to give you 5,014. You do the same thing for carbon dioxide. You are going to obtain the mass here over the total mass times 100%. Carbon dioxide was going to give you 16.219%. You do the same thing for water. The mass of water over the total mass times 100%. So that was going to give us 5,473%. Then you do the same thing for the sulfur dioxide. The mass of sulfur dioxide 0.1 over 18.09 times 100%. That was going to give us, in this case, 0.553%. All right, so add up everything. Your percentage is supposed to be at 100%. All right, so you're going to have your percentage taken at 100%. That is the idea. That is the whole idea of this section. This is how you are supposed to play around your questions in answering this type of a question to calculate the percentages. So the question was on the percentages, and you are considering by mass in this case. All right, so that was 12 marks. 12 marks for that. All right, 5.2, determine the height of a watt governor rotating at 80 revolutions per minute. All right, so here for a watt governor, if we are not given the arms, we are not given the mass of the arms, they are not considered. We are going to take our formula as the height is equal to the gravitational acceleration over omega squared, whereby omega is the speed in rad per second. So omega, it's 2 pi n over 60 in rad per second, all right? Whereby this n is the speed in revs per minute. Omega is another speed again, but is measured in rad per second. So you have to convert to rad per second. G is the gravitational acceleration at 9.81 meters per square second. So it means we're going to have H as 9.81 over omega squared. That's, remember, omega is 2 pi n. So it's going to be 2 pi times the speed. We have got the speed in revs per minute here. So it's going to be 80. We divide by 60. All right, everything is being squared. So we're going to square this. So that's it. We're going to have our H from there, which was going to be 0.13977 in meters. So that's something like 1, 2 is going to affect this to a 10 and a 4. So it's going to be 0.14. We round off properly here in meters. Yes, you can convert to millimeters if you want, but the direct unit that you are having on your answer, the direct unit there are meters. So you can just write your answer as meters as it is. So you're just supposed to be careful on your answering part. How are you going to answer your questions is very, very important. What are you considering as you are answering the question? What are you given from the information? Let's see the last question that we are given. So this is the velocity diagram concept. You're working with your turbines in this case. So let us just see the information and try to come up with a diagram that we are supposed to have. And that is 10 marks for that. So we are given that it's a single wheel of an impulse turbine is nozzles inclined at, so the nozzles, they are inclined at 23 degrees, which means we have got the nozzle angle, which is, remember, you're supposed to know your angles, guys. Your nozzle angle is your alpha, all right? That's your alpha to the plane of the wheel at an amount, and the amount of entering gas is 2 kilograms. So given the mass of the gas, which is 2 kilograms, the mean blade velocity is 160. So we are given U, and the relative, the blade angles are the same. All right, the coefficient of friction 0.9. All right, this can be a nice question actually. All right, this can be a nice question. Let's see. This can be a nice question the way I'm seeing here. All right, okay, let me just try and have my information here. So this is an impulse turbine. That's the first thing. We are talking about an impulse turbine where we know that it has with axial thrust, it has axial thrust in this case. All right, so let us just try to take our information. This is just question 6. So we're dealing with an impulse turbine, and it's a single stage that you are working with. The double stages for N6. All right, so this one is the one that is with axial thrust. So what is it that you're going to have in this case? You're just going to see that we are going to have the shorter side at the output, all right? So this is our sketch. So you're going to have the shorter part on the output and the bigger part on the input. These are the input that you're going to have. So for the meantime, I'm just going to label what is important and what we are given. The rest we'll see it on the actual diagram, all right? So we are given the blade here, I'm not the blade, but the nozzles that is alpha, the entering part, it's inclined. So it's taken at alpha, all right? The nozzle in this case is taken at, is inclined at this angle, which is 23 degrees. So we've got our alpha here, 23 degrees. All right, so that's 23 here. And all right, let's see what else we are given. We are given the mass of this gas, which is 2 kilograms. All right, then the mean blade velocity of 160. All right, so the mass here is 2 kilograms. And we are given the blade velocity here, which is our U, which is 160 meters per second. 160 meters per second, that's our U. Also, we have got what else? What else? Okay, we've done this. And the relative inlet velocity, 310 meters per second. This is the relative inlet, or I take note, this is the relative inlet at the side here. So we've got the relative inlet velocity, 310 meters per second. Then we've got as it enters, then we've got the relative outlet, which is the exit. All right. Then here, this is the flow velocity. This is our actual velocity in this case, which is at the inlet and also at the outlet, the actual velocity at the exit. Then we've got the flow velocities, this and that. All right. So here we're going to talk about those later on. We are given also that the blade inlet and outlet angles are the same. All right, so the blade inlet here is our blade. So remember, this is our blade, and here we talk about the turbine. So the blade inlet, which is theta, and the outlet, which is phi, in this case like this, they are equal. So we are saying theta is equal to phi. That is the blade inlet and the blade outlet. They are equal, all right? Okay, that's it. Then what else? What else? We are given the coefficient of friction, 0.9. Then draw a velocity diagram on a landscape by using a scale of 1 centimeter to 25 meters per second, all right? 1 centimeter to 25 meters per second. Remember, we've got the coefficient of friction there. So that is the information that you are given, all right? Our coefficient of friction was 0.9. Then we are given a scale 1 centimeter is equal to 25 meters per second. Draw this diagram. Okay. What are we going to do here? Let us start by the coefficient of friction. What is it that it can help us? Why are we given this? Remember I said K, which is the coefficient of friction, is equal to the relative exit velocity, which is the exit over the inlet, over the relative inlet velocity. We have got the inlet, so we can calculate the exit in this case, all right? So it's just going to substitute K, which is 0.9 is equal to the exit relative over the inlet relative of 310. So this is over 1 cross multiply. Thus, our relative exit velocity is going to be 310 times 0.9. So if you multiply properly, you're going to obtain 279 meters per second. So that's 279 meters per second. All right. So we have got the exit here, which is 279. All right. Sorry for that. 279 meters per second. Okay. All right, so that's it. This is a nice question, guys. As you can see, this question is very nice. Let us just convert also so that we can sketch, we can do the proper diagram. Since 1 centimeter represents 25 meters per second, here we're going to divide by 25. So 310, if we divide by 25, it's going to be 12,4. So that's 12,4 centimeters. 160 divided by 25, here is going to be 6,4. So that's 6,4 centimeters. 279 divided by 25, it's going to be 11, something like 11,16 centimeters. So this is going to approximate to 11,2 because we can't have direct 11,16. So it's just going to approximate to 11,2 centimeters. All right. So that's it. Yeah, that's our information. Yeah, that's our information. I think we are good. We are good. So let us just try have our instruments here for construction. Gonna need a ruler. Gonna need a protractor for measurement. All right, I think I inserted 2 here. Just gonna need 1. All right, so this is it, guys. Let's see. Okay, so we're gonna need first the reference line where we're gonna have our given velocities and the angles and so forth. All right, so if you just start from there, it's gonna be easier that way. All right, so let us start from our reference line. So from the reference line, you are going to mark your starting point. All right, so you're gonna mark your starting point to say, I'm starting at this point up to this point. All right, so this is just the starting point, guys, that you're gonna mark. You're gonna use your ruler, but in this case, I'm just gonna mark direct. So this is my starting point at the turbine here and at the blade. All right, so from here, we've got a distance of 6,4 centimeters. So you're gonna measure 6,4 centimeters. You place your ruler here. That's 6,4 is gonna be somewhere here. This is 6,5, so 6,4 just slightly here. All right, so that's where we are having our 6,4 in this case. All right, so meaning to say from this point to this point of the blade, we are having our U, which is 160 meters per second, and this line is 6,4 centimeters. 6,4 centimeters. All right, what else that we can construct so far? What we know is that there's an angle of 23 degrees that we are given at the that is the nozzle angle of 23. So you're gonna construct that. So let us measure 23. So we're gonna do this way. We need to measure 23. So this horizontal, this line must be at this point. This plus here, this where the intersection, this one must be at this point. So place this at this point here. You measure properly at this point here, something like this. All right. So if we are to measure that 23, that's gonna be, let me increase so that you can properly see where our 23 is. If I increase it, does not affect our angle. All right, so 23 is gonna be somewhere here. This is you are measuring along this 0 line. All right, so you are measuring from this line, that's 0 here. This is 180, which is at 0. So it's 0, 10, 20, 30, 40, 50, 60, and so on. So 23 is going to be somewhere 21, 2, 3, somewhere there before 24. Somewhere there, I'm just going to mark a point. So what you're going to do is to mark a point there. All right, I said somewhere here. All right, let's just hope this is not going to affect. All right, let's see, guys, what is happening here. Point, that's the idea there. All right, so I'm just going to mark here. Let's just hope I do not shift a little positive. But even if it happens that it is slightly not at the point, you are going to use exactly what you have from what you are constructing. You have got an allowance to do that. So you've got an allowance to do that. All right. So I'm just going to mark this. Sorry for that. I want to mark this direct angle. I want to mark this direct. Sorry for that. Okay. That's gonna be somewhere here. All right. Sorry for that, guys. I need it pass through exactly this point. All right. So it's gonna be like this. Okay. So let's try to increase this also. Increase it somewhere there. All right. So you're gonna mark passing through that point. And this line must be long enough because we do not know exactly where we are going to have the end point. We do not have the dimensions of this line. So just draw as much as you can. All right. So just something of that nature. All right. So if we are to consider this according to the information that we were given, guys, to be honest here, we are now stuck at this information. We are just, okay, this is where we are. We've got our alpha, which is the one that we used to construct this line of the input, the inlet absolute velocity. But the question is, how are we going to have the others? Okay, we have this distance. We know that there's 12,4 from this point of the blade, which is from the blade point here. If we measure 12,4, where it is going to reach with the line or to meet with the line, it means we can do that and have the starting point of what? Of our turbine. So here we're just going to measure 12,4 centimeters, all right? So from this point, we just gonna put it this way. At the end point of the blade here, this is what we need. This is where we want. We measure 12,4. All right, so this, all right, my dimensions, my ruler is upside down. I don't know what happened. Let me try put it this way so that we can see proper like this. All right, so from this point, I'm gonna place it at 0, then concentrate on 12,4. All right, so here, guys, it's gonna be too much. So you're gonna concentrate on 12,4. This one being at 0, this one must be at 0, then concentrate here 12,4. So this is somewhere around 12,5. All right, I shifted too much here. All right, that's somewhere 12, all right, a little bit. I'm just gonna move this one a little bit from this way. So this is 12,5. 12,4 can be somewhere. I'm just gonna, because my ruler is inside. So I'm just going to mark somewhere there. So my 12,4 is along this point here. All right, so this is where I'm gonna join back to the original point of the blade there. So I'm just gonna join these 2 points. All right, I'm too far. I'm supposed to be a little bit closer, or I can even join it this way so that I can properly see like this. All right, so it means that's where we are going to have our starting point here. So we used the length that we were given from what? From our inlet relative velocity, this one of 310, which is we use the distance of 12,4 to construct this line. Where it meets this line, it means we are having that as our point. All right, so this is what we're going to have. So this one, our relative inlet is gonna be 310 meters per second, which is 12,4 centimeters. Remember, this was 12,4 centimeters. All right, then we are told that here these two angles are equal. This angle and this angle that we're gonna have here, they are equal, but we do not know the value now. But because of this construction that we have made, we can we can measure the angle. Previously, we're not having the angle here, take note, it was just theta. But now we can measure this angle properly. All right, so you're gonna measure this angle and see what you're gonna have at the end. So if we are to measure this angle from this outer part, 0 going this direction is gonna be at 20 in this case. All right, this is what we have here. somewhere there. This will be 34, something like 34 there, because take note, this my line is so bold. So if you check here, it might be like it's at 35, but because of the boldness of this line, it's supposed to be at 34 degrees there. If we are to measure this angle properly from 0, 10, 0, 10, 20, 30, this is 35, so 34, just slightly there. The angle there is 34. Maybe you're obtaining 35, it's fine. Write that 35 as it is. All right, so here I'm obtaining 34 degrees. All right, so that's my theta. So my theta here is 34 degrees. But remember that theta, the blade inlet, is equal to the outlet. So we are going to draw from the outlet. We're going to measure 34 degrees again, just like the previous part, so that we can construct the line from there. So this will be 24 somewhere there. I'm just going to mark the point at 34. This is 35, 34 somewhere there. All right, so meaning to say we can construct the line of what? Of the exit relative velocity in this case, which is, we're going to do that. All right, so let's see what we're supposed to have at the end. All right, if we are to join these two, so here we're just going to extend a line, and also the distance there, you have it, so you can even measure it once. All right, so you're going to take it this way. That's something of this nature. So that's something like this. All right, so you must join passing at point, and this is supposed to be approximately somewhere there. All right, so that's what you're gonna have. And since we measured the angle of, remember this line was at an angle of 34. We are talking about the exit of the blade here, which is 34, which is outlet, right? But we also have the distance, so you can even mark here, because we're given that it's 11,2 approximately. 11,2, it was 11,16, but just measure 11,2 along this line. So 11,2 is somewhere here. So I'm just going to put this line 11,2 at this point. So this is 11,2 here. So I'm going to mark at 0 here. So meaning to say my point is supposed to be taken at 0. Okay, this is where I'm having my 0 there. My point is going to be taken at 0. All right, so this line from this point up to this point, it's 11,2 centimeters, but as we are focusing at is 11,1, but it's 11,2. That's what we can construct. So that's our exit in this case, which is 279 meters per second. That was 11,2 centimeters. All right. So the rest here we can just join. As we can see, the last part here, we just gonna join here. All right, here we're just gonna join from this point and this point. All right, so that's just joined there at the turbine to the end, which is at our exit in this case. All right, so there we're just gonna join. Okay, so if we measure this length here, it is going to be, if we measure, all right, let us put all that, that's 7 there, 7 centimeters. So this length is 7 centimeters. All right, so we've got a length of 7 centimeters. This is the exit, the absolute exit here. At the exit, 7 centimeters, then convert it to the scale, to the meters per second. Remember, 1 centimeter is 25 meters per second, so it's gonna be times 7, 7 times 25. That was going to give us 175 meters per second. So you multiply by 25. All right, the same thing you are going to do on the inlet here. On the inlet again, you're gonna measure this length. All right, you're gonna place your ruler, measure properly. Here, gonna place your ruler. You measure properly this from this point. It's only that, okay, my ruler here, the 0, I'm just gonna put my 0 here, it's fine. All right, so if I place my 0 at this point here up to this line, All right, let me extend here. All right, sorry for that. Just gonna extend a little bit here. All right, so if this is my 0 going to this line, as you can see, it's at 18. Yeah, that's 18 there. So we've got 18 centimeters that we are having. So that means our inlet is going to be at 18 centimeters. 18 centimeters, if we multiply by our scale, times 25, 18 times 25, that's 450 meters per second. All right. So what else? We also need the exit here, which is our beta, from the nozzle exit, which is beta. So we're gonna measure this one. We're just gonna measure. Take your protractor, measure properly. All right, this is too big. So you're gonna place it here and we measure our angle. This time we are measuring our angle from 0, 10 from the outer part. So this is 0, 10, 20, 30, 40, 50, 60. So that's at 66, which is 65. It was supposed to be actually at 65, all right? So like I said, you take the value that you're obtaining there, but this was supposed to be at 65 degrees, okay? Mine is 66. So I don't know what you're obtaining there. Let me know. All right, so constructing at an angle of 90 degrees from this point, we are going to construct at an angle of 90 degrees so that we obtain our velocities at the end. So at 90 degrees here, let me extend from this point. We're gonna construct at 90 degrees here. We do the same to these points again, back to 90 degrees to these points. That's 180 here, back to 90 degrees from this point here, back to 90 degrees. That means we're gonna pass through this point here at the point. All right, you do the same thing at 90 degrees. All right, at 90 degrees, this must be at 90 degrees here. Construct back here, we're gonna have our flow if we join at 90 straight at 90 there. All right, so we're gonna have our flow velocities at 90 degrees. All right, so that's the idea we are going to have. So meaning to say, if we join here, we're gonna have the flow velocity at the exit. We have got our flow velocity. We're just gonna join that 90. All right, down here, we're gonna have it just extend a little bit. All right, then here the 90 was passing through here from that point. The 90 was passing through this point here. Is that so? Yeah, that's maybe I marked a little bit aside, but the 90 is supposed to pass through here. All right, so that's 90. We also have at the inlet, the flow velocity here at the inlet at 90 degrees. We have our inlet at the end. All right, so that is it. We're gonna measure our inlet here. If we measure from this point 0, that's my 0 there at the top. So this is my 0 there at the top. So this line is going to be at 7. It's okay. From 0 here, it's going to meet at 7. So this line is 7 centimeters. So meaning to say our inlet flow velocity is going to be 7 times the scale. Remember, 1 centimeter is 25 meters per second. So it's going to be 7 times 25, which is 175 meters per second. All right. Let us go here to the exit. We do the same place here at 0. So it's going to be 0 to this point, which is at the exit. My 0 here is going to be 6,1, 2, 6,2. Yeah, something like that, 6,2, 6,3 there. Okay, so you have to measure properly 6,2, 6,3. So this was what, 6,3 centimeters. So it means our exit flow velocity is going to be 6,3 times 25, which is going to give us 157. comma, there's no comma there, there's comma 3, comma 5, 157,5, yes, that's comma 5 meters per second. All right, yeah, okay, that's what you're gonna have from your calculator. And what else? Angle here, the angle here. Okay, we can talk about the wheel velocities. Just gonna join horizontally here so that we obtain our wheel velocities, which is gonna be from the end point here to the end point that side, all right, at 0 there. So this will be our wheel in this case, all right. We're gonna have the wheel velocities in this case taken from this point up to that point, which is the whole of this line is the total wheel velocity. In this case, our total wheel velocity. Then if you want, you can talk about the inner part from this point here up to this point. And let me just do this way so that I can separate. We can talk about from this point here to this point, which is our exit wheel. Then from this point up to this point, this will be your inlet wheel. This one combined together from this point up to this point is the total wheel in this case. So if we had to measure properly, it was going to be 19,2, something like that. 19,2 centimeters, the whole of this line. So if you multiply by the scale of 25 meters per second, 19,2 times 25. So use the value that you're obtaining, guys, all right? Use the value that you're obtaining. You're going to obtain 450 meters per second from the 19,2. So I think our diagram is complete, guys. We've got everything that is important. What is important we have. So this is how you're supposed to have your diagram at the end. All right, 10 marks for that. Anyways, let's see. 6.21, the question there now is based on the diagram, determine the blade inlet angle. All right, so the blade inlet, remember we got it here, our theta, which is the blade. So theta here is 34. So we already have this. So that's 6.21. So the blade inlet is 34 degrees. The blade outlet is also 34 degrees, okay? Then from the diagram, they want us to have the flow inlet velocity in meters per second. So the flow inlet, this is the velocity of the flow inlet, which is here, the flow inlet 175. We calculated this from 7 centimeters times the scale we got 175. So this one we are given. So the inlet velocity flow is gonna be 175 meters per second. All right. Then the other question, it was to calculate or to determine by means of the diagram on 6.3, calculate the power in kilowatt. All right, so the power can be taken from the total flow velocity. We have got, the wheel velocity in this case. So we're gonna take from this formula. I explained also this formula that the power, simply use this formula, the mass times the blade velocity times the total wheel velocity in this case. All right, that's it. We've got everything. Remember the mass we are given, the mass of air, which is 2 kilograms in this case. So we're going to have 2 kilograms. There we are given as kilograms. So that's 2, not 0.2, but 2 kilograms times our blade velocity, the mean blade velocity, which is 160 meters per second. So I've got 160 meters per second times the total wheel, which is 480. Okay, so that is going to give us the power, which is 153,600 watts. But we are supposed to have this in, they said in kilowatts. So to convert this to kilowatts, going to divide by 1,000, which is 153.6 in kilowatts in this case. All right. So that was it. That was it, guys, in our paper. That was it. 100 marks for that. 100 marks for that. Okay. All right. So as you can see, guys, you can actually totalize power machines in 5. you can totalize this subject. This is one of the subjects that you can score 90% in exam, 90%, as long you know your manipulation from your mathematics. Just also play around with your mathematics. It's a direct thing that you have, something that is direct, that you just need to know how to play around with your formulas, manipulating of formulas, and the substitution conversion of units at the end. Read the question properly. How are you asked the question? Give your answer in what? Is it in cubic meters per second, cubic meters per kg, or per watt? The units are very, very important in power machines N5 and also in power machines N6. So that's it, guys. We will meet again. Let us just continue to share our platform to our friends and colleagues.